Hello friends, let me welcome you all to my 6th video on the chapter phenols, alcohols and ethers, right? In the previous videos, we have completed the discussion on alcohols. Now in the today's discussion, in the today's video, we'll see the discussion on we'll start the discussion on the phenols. One more kind of hydroxy derivatives of hydrocarbons, right? There are hydroxy derivatives of hydrocarbons in which the hydroxyl group is directly attached to the benzene ring. The hydroxyl group is directly attached to the benzene ring. And that class of organic compounds are called as, yes, it is phenols. Benzene to which, yes, it is OH group is directly attached, and that is what we call it as phenol it is. Or you can go for any compound where we have, yes, it is OH groups directly attached to the benzene ring. Look at this. So this is, we have two fused benzene rings, that is naphthalene. To this, we have OH group is connected. This is also phenol, because OH group is directly attached to the benzene ring. Any organic compound where one or more hydroxyl groups are directly attached to the benzene ring, that is what we call it as phenols. So this is what we call it as, this is also phenol. These are all the examples for the compounds where OH group is directly attached to the benzene ring. That is the sp2 hybridized carbon atoms of benzene ring. Because in the case of benzene, all carbon atoms are sp2 hybridized, right? Is it not? Because of the hybridized carbon atom of sp2 hybridized carbon atom of, yes, it is that is benzene ring, right? And as far as in the case of phenol, CO bond is concerned, right? We have, this is carbon and this is oxygen, this is CO bond, and of course we have OH bond, is it not? As in the case of alcohols, right? In the case of phenols, this carbon atom is sp2 hybridized, right? This oxygen is what we call it as sp3 hybridized. Okay, now that means the carbon to oxygen single bond is produced by overlapping of half-filled sp2 hybrid orbital of carbon and half-filled sp3 hybrid orbital of oxygen. And that results in the formation of sigma bond there. And here it is, this OH bond is produced by overlapping of half-filled sp3 hybrid orbital of yes, it is oxygen and s orbital of hydrogen. And this is what we call it as something about, yes, it is phenols there. Whereas here also you will find this COH bond, but this carbon is sp3 hybridized, this oxygen is sp3 hybridized, and here it is s orbital, right? So also this is the main difference between as far as, yes, it is alcohols and phenols are concerned. And of course the sp2 hybridized carbon atom is of course the carbon atom of the benzene ring. So this is what we call it as something about the phenols, that is hydroxy derivatives of benzene, where the one or more hydroxyl groups will be directly attached to the benzene ring, and that is what we call it. This class of organic compounds, they have got their own importance in our day-to-day life. Why should we study these phenols? What are the advantages of these phenols? If you ask that question, I'll give many applications as far as phenols are concerned. This phenol is used, in the manufacture of, yes, it is phenol formaldehyde polymer. This phenol is used in the manufacture of phenol formaldehyde polymer, and that is called as bakelite. That is called as bakelite, and of course one of the thermosetting plastics. This is one of the thermosetting plastics used in the manufacture of the devices which will be working under high temperatures. For example, you take iron box, the iron box, the handles of the iron box will be made up of bakelite polymer because it can withstand very high temperature. Like that, bakelite is very useful, yes, it is thermosetting plastics, right? So that is manufactured starting from phenol. Apart from that, phenol is used in the manufacture of phenolphthalein. Phenol is used in the manufacture of phenolphthalein. One of the dyes, one of the colored organic compound. Yes, this phenolphthalein is used as an indicator in various titrations, in acid-base titrations, this phenolphthalein is used as an indicator. That is another application of this phenol, right? Apart from that, this phenol is used in the manufacture of cyclohexanol. This phenol is used in the manufacture of cyclohexanol, right? And this cyclohexanol is a very good solvent for, yes, it is. It's a solvent for rubber. Yes, it is phenol itself. And the fourth one, it is, phenol is used as a preservative for ink. It is used for, yes, it is used as ink, preservative for ink, of course, because this phenol, yes, it is prevents ink from spoiling. Yes, or you can say that it will prevent coagulation of blue colored substance, that is dissolved in, yes, it is ink there. If phenol is not added, that blue colored organic compound will be precipitated after a few days. Because of that, this particular this particular phenol is added to, yes, it is ink in order to avoid coagulation of, yes, it is the blue colored dye in ink, and that is what we call it as, it is used as a preservative for ink. Apart from that, phenol is used in the manufacture of various drugs like aspirin, or you can say Celol. These are the chemical substances used in the treatment of various Celol and phenacetin. These are the drugs which will be manufactured starting from phenol itself. These are the drugs which will be manufactured starting from phenol itself. Apart from that, phenol is used in the manufacture of picric acid. Picric acid is an explosive compound. It is used as an explosive compound. That is another application. This picric acid can be manufactured starting from phenol itself. And because of that, this phenol finds many applications as far as our day-to-day activities are concerned. Because of that, the study of phenols is very, very. With that introduction, we'll go for the, yes, it is the classification of phenols first. The first discussion is classification of phenols. And this classification is very simple, depending upon the number of OH groups attached to the benzene ring. That is classification of phenols. Depending upon the number of OH groups attached to the benzene ring, phenols are classified into three types. One, it will be monohydric phenols. Monohydric phenols. So this is one of the types of phenols. In the case of monohydric phenols, you'll find one OH group directly attached to the benzene ring per molecule, right? The molecule contains one OH group, that is what we call it as monohydric phenol. So this is one example for the, yes, it is phenol, and that is monohydric phenol. And of course, here we have, yes, it is, this is what we call it as another example for the monohydric phenol, and it is called as orthocresol. And this is also called as orthocresol. And of course, apart from that, we have, yes, it is one more monohydric phenol, and that is metocresol. This is metocresol. This is metocresol because OH groups and of course the CH3 groups are at the meta position to each other. And that is, apart from that, we have this is, and this is what we call it as paracresol. This is paracresol. And that is OH group and CH3 groups are at the para position to each other. And of course, if you want to understand that particular, or this is, say for example, this is benzene ring attached with X, okay na? So this is number 1, this is number 2, this is number 3, 4, 5 and 6, right? Now at this moment, look here, yes, if X is not there, all carbon atoms are identical. If X is not attached to benzene ring, there is no difference among the carbon atoms present in, yes, it is benzene ring, and of course all are identical. But when X is attached to benzene ring, different types of carbon atoms are created. Yes, how it is, look here. If X is attached to this carbon atom, look at this, these two carbon atoms, that is 2 and 6. 2 and 6, they are equidistant from X. They are equidistant from X. Again, 3 and 5. Equidistance from X, and of course 4 is at a particular distance from X, is it not? Means influence of X on 2 and 6 is same. Now the influence of X on 2 and 6 is different from that on the 3 and 5. Therefore 2, 6 positions are called as ortho positions. 3, 5 positions are called as meta positions, right? 4th position is called as para position, right? And ortho, meta and para positions will be decided on the basis of, yes, it is position of X. And of course, if I say, look at this, if benzene is attached with X here, right? If benzene is attached, if X is attached to this particular position, of course, no difference between this compound and this compound. Still, let me show you that this is position number 1, this is number 2, this is number 3, this is 4, this is 5, and this is 6, right? And then once again, 2, 6 positions are ortho positions, 3, 5 positions are meta position, and 4th position is para position. Yes. ಯಾಕಂದ್ರೆ ಕೆಲವು ಸ್ಟೂಡೆಂಟ್ಸ್ ಏನಾಗಿರ್ತಾರೆ ಅಂದ್ರೆ ಈ ತರ ಫಿಕ್ಸ್ ಮಾಡಿರ್ತಾರೆ, ಇದೇ ಆರ್ಥೋ ಪೊಸಿಷನ್, ಇದೇ ಮೆಟಾ ಪೊಸಿಷನ್, ಇದೇ ಪ್ಯಾರಾ ಪೊಸಿಷನ್ಸ್ ಅಂತ ಫಿಕ್ಸ್ ಆಗಿರ್ತಾರೆ. ಹಾಗಲ್ಲ, the ortho para positions will be decided on the basis of the substituent already present in benzene ring. Orthopara meta positions will be decided on the basis of the substituents already present in benzene ring. If X is here, these two are ortho, these two are meta, and this will be para. If substituent is here, these two are ortho, these two are meta, and it will be para. So this is what we call it as, yes, it is ortho, meta, and para positions, right? Yes, these are the examples for the, yes, it is the monohydric phenols, right? Okay, now where all these compounds are characterized by one OH group per molecule. Yes, one OH group per molecule. Howda? And I am going to discuss IUPAC names also under the same headline. Yes, and of course in the IUPAC system, phenols will be named. Yes, it is as the derivatives of benzene, or they are the derivatives of phenol, because phenol itself is taken as IUPAC name of this compound. Actually, this phenol is obtained from the common system. The name is obtained from the common system, but in this common name, phenol, is written as IUPAC name. You can name it as hydroxybenzene. You can name it as hydroxybenzene in IUPAC system, but phenol will be written as a IUPAC name. What about this compound? Yes. What about this? This is orthocresol. Orthocresol, it is common name. But of course, in IUPAC system, it is 2-methylphenol. It will be 2-methylphenol. This is the IUPAC name of it. This is first position and this is second position, because one will be given to the carbon atom carrying functional group and of course phenolic group, and therefore it is 2-methylphenol. Yes. Or you can say you go for this 2-methyl. Yes, it is 1-hydroxybenzene. That is 1-hydroxy. Yes, it is 2-methyl. 1-hydroxy 2-methylbenzene. You can also take it as a IUPAC name of this. And of course, this as far as this one is concerned, this is number 1, this is number 2, this is 3. Therefore, it is 3-methylphenol. This will be 3-methylphenol is the IUPAC name of this. And it will be 1, 2, 3, 4. It will be 4-methyl. It will be 4-methylphenol is the IUPAC name of phenol. Yes. So this is common names as well as IUPAC name. And of course, all compounds are coming under what we call it as monohydric. Yes, it is phenols, right? Nan classification allane nomenclature kuda helta idini. Okay na? I don't discuss nomenclature separately, right? So this is what we call it as the classification of phenols, and of course monohydric phenols. And in addition to that, we have yes, it is the IUPAC names also, right? So that will be dihydric phenols. Dihydric phenols are characterized by 2, yes, it is hydroxyl groups per molecule. 2 hydroxyl groups will be directly attached to the benzene ring, and of course it will be right. It will be right. This is OH group, and it will be OH group. Yes. Look at this. These two OH groups are the ortho position to each other, and it will be called as catechol in common system, right? Or you can say it is 1,2 dihydroxybenzene. It will be 1,2 dihydroxybenzene. This is 1, this is 2, right? 1,2 dihydroxybenzene. Athava, yes, it is. This is benzene. Yes, 1,2 diol. Because we have diol, because we have 2 OH groups. Benzene 1,2 diol. This is what we call it as different names. These two are IUPAC names, and it will be catechol is a common name. So 1,2 dihydroxybenzene, or you can say that benzene 1,2 diol. This is what we call dihydric phenol. Apart from that, we have this is OH, and it will be OH. 2 OH groups are at the meta position to each other. Here 2 OH groups are at the ortho position to each other. This can also be equal to like this. Yeah, this is OH and this is OH. Idu kuda catechol. Matte bere bere anta ankobedi. Idu kuda catechol. Yes, totally 2 OH groups are at the 1,2 positions, right? Ortho position to each other. Yes, this is what we call resorcinol. This is what we call it as resorcinol, right? Or you can say this is 1,3 dihydroxybenzene. 1,3 dihydroxybenzene. It is 1,3 dihydroxybenzene or benzene. Really, 1,3 diol. Benzene 1,3 diol, because 2 OH groups are at the 1,3 positions, right? 1,3 diol. Yes. Apart from that, we have, yes, it is one more example for the dihydric phenol. We have 2 OH groups at para position to each other, and it will be, yes, it is hydroxyphenol. Yes, phenol, sorry, this is phenol. This is called as phenol, right? Or you can say this is 1,4-dihydroxybenzene. 1,4-dihydroxybenzene. IUPAC name, right? Common name is benzene. Sorry, IUPAC name is benzene 1,4-diol. Benzene 1,4-diol. Common name is phenol. It is common name is phenol. So this is what we call it as the examples for the dihydric phenols and their common names and IUPAC names, right? With that information, we'll go for the trihydric phenols. The examples for the trihydric phenols, right? It is trihydric phenols now. It is trihydric phenols, right? Look at this. Trihydric phenols, right? Trihydric phenols are characterized by 3 OH groups per molecule, right? There will be 3 OH groups directly attached to the benzene ring, right? So one such example is, this is OH, and it will be OH, right? 3 OH groups are directly attached to the benzene ring, right? 3 OH groups are directly attached to the benzene ring, right? So this is what we call it as, yes, it is pyrogalol. It is pyrogalol is the common name of this compound. Or you can say benzene. Hey, 1, 2, 3. 1, 2, 3 triol. Benzene 1, 2, 3 triol, because 3 OH groups per molecule. Yes. Or 1, 2, 3 trihydroxybenzene. You can also write it as 1, 2, 3 trihydroxybenzene, right? Look at this. One more example for the, yes, it is. Okay, this is trihydroxybenzene. This is hydroxyquinol. This is hydroxyquinol. This is hydroxyquinol. Yes, very interesting compound it is, because if OH group is not there, it will be quinol, right? Okay, now if OH group is not there, it will be quinol. If OH group is present, it will be hydroxyquinol. And of course, it is benzene. Benzene, yes, it is 1, 2 and 4. This is 1, this is 2 and this is 4. 1, 2, 4, yes, it is triol. And this is what we call IUPAC name of this, benzene 1, 2, 4 triol. ನೀವು ಹೇಳ್ಬೋದು 1, 2, 4 ಈ ಕಡೆಯಿಂದ ಕೊಟ್ಟರೆ 1, 2, 3 ಆಗುತ್ತೆ, ಹೌದಾ? ಹೌದಾನೆ? ಸಮ್ ಆಫ್ ದಿ ಲೊಕೇಟ್ಸ್ ಏನಾಗುತ್ತೆ ನೋಡಿ. ಹೀಗಾದ್ರೆ 1 + 2 + 4 = ಎಷ್ಟಾಗುತ್ತೆ? 7 ಆಗುತ್ತೆ. ಹೀಗಾದ್ರೆ ರಿವರ್ಸ್ ಆದ್ರೆ 1 + 1, 2, 3 1 + 3 ಆಗುತ್ತೆ. 1, 2, 3 ಆಮೇಲೆ +4 ಎಷ್ಟಾಯ್ತು ಅಲ್ಲಿಗೆ? 8 ಆಗುತ್ತೆ. Which is preferred? Lowest sum row. Therefore it is, this has to be followed, and therefore it is benzene 1, 2, 4 triol. Now it is one more example for the trihydric phenol, and that is symmetrical phenol. It is fluoroglycinol. That is, it will be fluoroglycinol. This is fluoroglycinol. Yes, this is pyrogalol. That is fluoroglycinol. And of course, its IUPAC name is benzene. Yes, it is 1, 2, 3, 4, 5, 6. 1, 3, 5. Because we have OH groups at the first, third, and fifth carbon atom. 1, 3, 5 triol. And this is what we call it as IUPAC name of fluoroglycinol. These are the examples for what we call it as trihydric phenols. They are the examples for the trihydric phenols, right? We'll go for the next topic, that is structure of phenols, right? So we already studied the structure of alcohols, right? So we compared the structure of alcohols with that of the water. We compared structure of phenols, alcohols with that of the water. Here also structure of phenol with that of the water. Yes, look at this. And this is water. The shape of the water is, yes, this is inverted V shape. This is V. Inverted V shape or the bent shape. Okay, now. Okay, with a lone pair of electrons on the oxygen, with 2 lone pairs on the oxygen, right? And oxygen atom is sp3 hybridized. Your oxygen atom is sp3 hybridized, right? Inverted V shape with the oxygen atom sp3 hybridized. If one of the hydrogen atoms is replaced by, yes, it is, if one of the hydrogen atoms is replaced by benzene ring, it will become phenol. It will become phenol. Yes, look at this. Here, the bond angle is 109 degree, almost similar to that of alcohols. In the case of alcohols, it is 108.9 degree. In the case of alcohols, that is methanol. But in the case of phenol, it is less than regular tetrahedral angle, 109 degree 28 minutes, because lone pair repulsion dominates lone pair bond pair repulsion, right? One more interesting observation here is, in the case of phenol, look at this. This is CO bond, yes. This is CO bond, that is CO, yes. CO bond length of, yes, it is CO bond length of phenol is, yes, it is around 136 pm. It will be shorter than CO bond length of alcohol. CO bond length of methanol, that is CH3OH, and it will be around 142 pm. Look at this. This is the interesting observation. The CO bond length in phenol is around 136 pm, and in the case of it is alcohol, so methanol, it will be 142 pm. Yes. Why it is so? Why CO bond length in phenol is shorter than that in the case of methanol? And the reason is quite clear, because in the case of phenol, look at this. In the case of phenol, this is phenol, right? Here it is OH bond, right? Here it is OH bond, right? Here we have oxygen carries lone pair of electrons. Two lone pairs are there, yes. And these lone pair of electrons on the oxygen will be taken part in resonance. The lone pair of electrons or unshared pair of electrons on the oxygen will take part in resonance with the pi electrons of the benzene ring, and that induces, because of that, because of that resonance, these lone pair of electrons will be in conjugation with the double bond of the benzene ring. That induces partial double bond character between, yes, it is oxygen and carbon. Single bond is converted to double bond, yes. As that electrons are moving away from oxygen, it will get positive charge, yes. And your electrons will be moving over this, and this particular point will get negative charge. And look at this. This is the resonance structure of phenol, where you will find the partial double bond character. Carbon to oxygen single bond is converted to carbon to oxygen double bond. That is, as the number of bonds between two atoms increases, bond length decreases. For example, C single bond C, C double bond C, C triple bond C anta idre. C single bond length is, yes, it is larger than C double bond length. C double bond length is larger than C triple bond. As the number of bonds between two atoms increases, bond length decreases, because the force of attraction increases. As the bond order, what we call it as the number of bonds between two atoms increases, force of attraction between two atoms increases, then atoms are coming closer and closer, therefore bond length decreases. So here, due to the partial double bond character, bond length decreases. And that double bond character is due to the resonance of unshared pair of electrons on the oxygen with the pi electrons of the benzene ring. Apart from that, in the case of, yes, it is phenol, oxygen is directly attached to the sp2 hybridized carbon atom. In the case of phenols, carbon is directly attached to the sp2 hybridized, that is, oxygen is directly attached to the sp2 hybridized carbon. Oxygen is directly attached to the sp2 hybridized carbon atom. Whereas in the case of alcohol, like methanol, oxygen is directly attached to the sp3 hybridized carbon atom. Here, oxygen is directly attached to the sp2 hybridized carbon, and oxygen is directly attached to the sp3 hybridized carbon atom. I said sp2 hybridized carbon atom is more electronegative than sp3 hybridized carbon atom. Therefore, here the force of attraction is maximum, that because of high electronegativity, it will attract sigma bonds, it will attract sigma electron plus towards it, thereby the bond is very, very strong, and of course bond length decreases, right? The CO bond is stronger than that in the case of CO bond in the case of, yes, it is methanol, due to high electronegativity of sp2 hybridized carbon atom in phenol. Whereas in the case of methanol, oxygen is directly attached to the sp3 hybridized carbon atom of, yes, it is methanol, which is less electronegative than that of the sp2 hybridized carbon atom of phenol. And that is because of these two reasons, the CO bond length in phenol is shorter than that in the case of methanol. So this is what we call it as structure of phenols, right? With that information, let us move on to the next topic, that is preparation of phenols. Let us move on to the next topic, that is preparation of phenols, right? Preparation of phenols. And of course, as per your NCERT textbook, we are supposed to study 4 methods. You are supposed to study 4 methods as far as preparation of phenols are concerned, and that is, first method is from chlorobenzene, and that is from chlorobenzene, right? The first method is from chlorobenzene, and the method is called that is Douse process. Dow is a name of the scientist who introduced that particular process, that is Douse process, right? In the Douse process, look here, right? Yes, when chlorobenzene, this is chlorobenzene, right? And this is chlorobenzene. When chlorobenzene is heated with, yes, it is sodium hydroxide solution, right? When chlorobenzene is heated with sodium hydroxide solution, right? Nucleophilic substitution takes place and chloro group is replaced by OH group. When chlorobenzene is strongly heated with, yes, it is sodium hydroxide solution, yes, and nucleophilic substitution takes place under drastic conditions, because you know haloarenes do not undergo nucleophilic substitution reactions easily, and because of that, you know, you are supposed to maintain very high temperature and very high pressure. How the very high temperature and very high pressure, and of course the high temperature of around 623 kelvins, high temperature of 623 kelvins, high pressure of 300 atmospheres. These are the drastic conditions required. Then chloro group is replaced by NaOH, but due to the presence of NaOH, you know, yes, it is phenol will be in the form of sodium phenate. You are going to get sodium phenate first. You are going to get sodium phenate. Remember, ನೀವು ಡೈರೆಕ್ಟ್ ಆಗಿ ಈ ತರ ಕ್ಲೋರೋ ಗ್ರೂಪ್ ಇಸ್ ರಿಪ್ಲೇಸ್ಡ್ ಬೈ OH group ಅಂತ ತಕ್ಷಣ ಫಿನಾಲ್ ಬರುತ್ತೆ, ನಾನು ಇಲ್ಲ ಅಂತ ಹೇಳ್ತಲ್ಲ, ಬಿಕಾಸ್ ವೆನ್ ಫಿನಾಲ್ ಇಸ್ ದೇರ್ ಇನ್ ಪ್ರೆಸೆನ್ಸ್ ಆಫ್ NaOH ಪ್ರೆಸೆನ್ಸ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಫಿನಾಲ್ ವಿಲ್ ಬಿ ಇನ್ ದ ಫಾರ್ಮ್ ಆಫ್, yes, it is sodium phenate, and of course this is acid and this is base, and H plus will be replaced by Na, right? Okay, ಹಾಗಾಗಿ phenol in presence of NaOH will be in the form of a salt, that is sodium phenate ಅಥವಾ sodium phenoxide. Okay, na? And when this sodium phenoxide is hydrolyzed in presence of dilute HCl, when sodium phenate is hydrolyzed, the sodium phenoxide is hydrolyzed in presence of, yes, it is dilute HCl, and of course phenol is regenerated, and of course you are going to get phenol along with the formation of NaCl. So this is what we call it as the equation that is needed to this particular reaction, that is okay na, right? When chlorobenzene reacts with NaOH, right, you are going to get sodium phenate. Phenol barutte in presence of NaOH, it will be in the form of sodium phenate. When this sodium phenate is hydrolyzed with HCl, strong acid it is, HCl is a strong acid, displaces weak acid like phenol from its compound sodium phenate, and that's why you are going to get phenol. That is what we call it as the preparation from chlorobenzene, right? And this is what we call it as Douse process, and conditions are very important. Why should we maintain very high temperature and very high pressure antandre haloarenes do not undergo nucleophilic substitution reactions easily. They undergo nucleophilic substitution reactions under drastic conditions. You know the reason, because of double bond character between carbon and chlorine. So that is what we call it as Douse process, right? Now at this moment we will go for the next one, that is preparation from benzene sulphonic acid. That is preparation from benzene sulphonic acid. That will see. Preparation from benzene sulphonic acid. While writing organic equations, you know, don't worry about, yes, it is balancing organic equations, right? Okay na, hagagi, so that is preparation from benzene sulphonic acid, right? And as far as benzene sulphonic acid, yes, it is it can be obtained by, yes, it is benzene, right? When benzene reacts with fuming sulfuric acid, that is concentrated sulfuric acid, right? This is, yes, it is oleum, we call it as. Upon heating, when benzene is heated with oleum, that is, oleum is the concentrated sulfuric acid saturated with sulfur trioxide, concentrated sulfuric acid saturated with sulfur trioxide, that is called oleum, and of course it is fuming sulfuric acid, right? And of course sulfonation takes place, and that results in the formation of, yes, it is benzene sulphonic acid. This is benzene sulphonic acid. This is benzene sulphonic acid, right? This is benzene sulphonic acid. Benzene sulphonic acid is heated with, yes, it is fused with sodium hydroxide, yes, molten sodium hydroxide. When this benzene sulphonic acid is heated with, yes, it is fused with sodium hydroxide, yes, fused with anta word idella adu important ಇಲ್ಲಿ ಅಥವಾ when sodium benzene sulphonic acid is heated with molten NaOH, yes, melted N, you are going to get, yes it is, you are going to get, yes it is, sodium phenate you are going to get, sodium phenate, and of course with the loss of NaHSO3 from this particular group, from this particular benzene sulphonic acid, NaHSO3 is going out, and of course 2 NaOH, and of course plus H2O ಬರುತ್ತೆ. This is what we call it as sodium phenate ಅಂತ ಕರಿತೀವಿ. Sodium phenate. ನಿಮಗೆ ಇದನ್ನ ಸಪರೇಟ್ ಆಗಿ ತೋರಿಸ್ತೀನಿ ನೋಡಿ. This is what we call it as SO3Na. So SO3H alva. And of course you are going to get NaOH, right? Okay na? NaHSO3, NaHSO3, right? Again, then you are going to get OH. ಹೌದಲ್ವಾ? ಇದೇ ನೋಡಿ ಅದು. And one more NaOH molecule is there. In presence of NaOH, phenol is converted to what? In presence of NaOH, phenol is converted to what? Sodium phenate. This is acid and this is base. Sodium phenate, and you got sodium phenate. That's why 2 NaOH. Okay, now one NaOH molecule converts this into this, and another NaOH molecule converts this into this, and that is sodium phenate is a product. When sodium phenate is formed, and when sodium phenate is hydrolyzed, right, in presence of dilute HCl, when sodium phenate is hydrolyzed in presence of dilute HCl, and you are going to get, yes it is phenol plus what is that? NaCl. Okay na? So once a little one ಸ್ವಲ್ಪ ಗಮನದಲ್ಲಿ ಇಟ್ಕೊಳ್ಳಿ. ನಾನು ಫಿನಾಲ್ ಅನ್ನು ಕೆಲವು ಸರಿ ಹೀಗೆ ಬರಿತೀನಿ, ಕೆಲವು ಸರಿ ಹೀಗೆ ಬರಿತೀನಿ. No problem, because you can keep OH anywhere in this molecule. No problem, because both are, all are identical. All carbon atoms are identical, and of course this is phenol, this is also phenol, this is also phenol, and of course this is what we call it as phenol. So this is what we call second method for the preparation of phenols, that is from, yes it is benzene sulphonic acid, right? Yes. Next we'll go for the next one, that is preparation from benzene diazonium salts. Preparation from benzene diazonium salts. You studied that in the chapter haloalkanes and haloarenes, where you prepared benzene diazonium chloride starting from aniline, right? That is preparation from benzene diazonium salts. And this is the third method for the preparation of, yes it is phenols. And of course when aniline, this is aniline, right? This is aniline. When it reacts with, sodium nitrite in dilute HCl, and of course at about 0 degree to 5 degrees Celsius, that is 0 to 5 degrees Celsius, right? At about 0 to 5 degrees Celsius, right? 273 to 278 Kelvin's temperature, right? And under these conditions, you are going to get, yes it is benzene diazonium salt. This is plus, and of course it will be minus. This is benzene diazonium chloride. Look at this, N triple bond N, N triple bond N, and this nitrogen will get positive charge, and of course nitrogen attached to benzene will have a positive charge, yes. Another nitrogen will have a zero charge, Cl will get a minus charge, yes. This is called benzene diazonium chloride. So this is one of the useful compounds. It can be used for the preparation of, yes it is, it can be used for the preparation of varieties of aromatic compounds, that is benzene diazonium chloride, yes. When this benzene diazonium chloride is warmed with water, yes, this nitrogen gas is taken out, Cl is replaced by OH, and of course you are going to get phenol. Plus nitrogen. Chloro group is replaced by H plus, and OH will be attached to benzene, and of course you are going to get HCl. So this is what we call it as, yes it is preparation from, yes it is benzene diazonium chloride. Aniline will be converted to benzene diazonium chloride by reacting with sodium nitrate in dilute HCl at 0 to 5 degrees Celsius. When it is warmed with, this is warm, when it is warmed with water, the whole azo group is replaced by OH group along with the formation of, yes it is HCl. This source of OH group, the benzene ring attack by replacing azo group. Azo group is removed in the form of N2, Cl minus will be removed in the form of HCl. So that is what we call preparation from benzene diazonium chloride, salts. The last method for the preparation and as per your NCERT textbook is concerned, and that is very important as far as examination point of view is concerned, that is cumin process for the preparation of phenol, and that is preparation from cumin, that is preparation from cumin. Preparation from cumin. Fourth method for the preparation of phenols. And that is fourth method for the preparation of phenols, that is preparation from cumin. As far as cumin is concerned, this is cumin is isopropyl benzene, and this is isopropyl benzene. You call it as cumin, and this is a compound. This is also named as isopropyl benzene, and this is chemical name of this particular compound, isopropyl benzene. Athwa you name it as 2-phenyl propane. Its IUPAC name is 2-phenyl propane. Nodi 1, 2, 3 2-phenyl. Second position phenyl group is 2-phenyl propane athwa isopropyl benzene. Yes, when oxygen gas is bubbled through this particular benzene, that is cumin. When oxygen gas is bubbled through the cumin athwa isopropyl benzene, ಏನಾಗುತ್ತೆ? Oxidation of the CH bond takes place. Oxidation of the CH bond takes place. Correct ನೋಡಿ? The CH bond is undergoing oxidation. Yes, and that results in, look at this. This is CH3 and this is CH3, right? And of course, look at this. O2 is will be oxidizing the CH bond and gets converted to COOH. Why this CH bond is affected by the oxygen antandre? Because this CH bond is weak because it is directly attached to the benzene that acts like an electron withdrawing group. Hagagi CH bond is weak bond, undergoes oxidation, and you are going to get this is cumin hydroperoxide. This is cumin hydroperoxide. This is cumin hydroperoxide. Don't be under the impression that many students will write like this. Yes, it is. Adanna COOH anta idara barbiಡ್ತಾರೆ. No, look at this. This tertiary carbon atom is oxidizing here, and it will be in the form of peroxide. Oxygen atoms. When two oxygen atoms are linked through a single bond directly, and that is peroxide linkage. Okay, now there is a direct linkage between two oxygen atoms. That is what we call peroxide linkage. Yes. When this cumin hydroperoxide is, it is hydrolyzed. When this cumin hydroperoxide is hydrolyzed, acid hydrolysis in presence of dilute HCl, and of course this will be taken out in the form of acetone. Yes, and along with that, you will left with what? Yes, which will be connected to this benzene ring, and it is what we call it as phenol. Yes, this is what we call it as phenol. And in addition to that, you will get a very useful side product, that is acetone. In addition to phenol, you get this acetone propane 2-one. You are going to get a very useful that is the side product, that is propane 2-one acetone, and that's why this reaction finds it will be largely used for the manufacture of phenol throughout the world, and that is what we call it as cumin process for the manufacture of phenol, athwa preparation manufacture of phenol from cumin. When cumin is oxidized, you are going to get cumin hydroperoxide, which will be hydrolyzed by using dilute HCl to form. Yes, it is. So this is what we call preparation of phenol. In the next video, we'll see. Yes, it is physical properties and chemical properties of phenol. Agboda? That's all, right?